A copper ring has a radius of 200 centimeters at 50 degrees Celsius. Find its radius at 550 degrees Celsius. Given its linear expansion coefficient is 17 times 10 to the power minus 6 Kelvin inverse. Now this number called the linear expansion coefficient is just a number that tells us how much something expands on heating. So this number is telling me or telling us how much copper expands on heating. And here's the way to think about this. So imagine you had exactly 1 meter long copper wire. So assume this is copper. And say you heat it up, increase its temperature by exactly 1 Kelvin. Then the whole thing would expand by that number. That's what this number really is. And similarly, you could also cool it down by 1 Kelvin. Say you decrease the temperature by 1 Kelvin, then the rod would shrink. And again, now the rod would shrink by exactly that value. That's how you think about this number. All right, and we have spoken about this in a previous video in detail. And so if this sounded a little bit confusing to you, or maybe you require more clarity on that, it would be a great idea to watch that video first and then come back over here. So with this info, please pause the video and see if you can try and solve this yourself, and then we'll solve it together. All right, let's do it. Let's first write down what's given to us. We have a copper ring which has a radius of 200 centimeters. So here is our copper ring. It has a radius. Let's call that radius as R. And that radius R is 200 centimeters. At 50 degrees Celsius, which means the current temperature T is 50 degrees Celsius. We need to find its radius at 550 degrees Celsius. So you understand what's going on? We are heating it up and its temperature is increasing. And so what happens? So let's see. If you were to heat this up, then the temperature would increase and it would expand, and you might see something like this. And so notice its radius also starts increasing as it expands. And so what we need to do is, when the temperature has reached 550 degrees Celsius, we need to calculate what the new radius is going to be, okay? So we would be interested in the change in the temperature, right? That's what matters to us, not what the temperature is, but how much has the temperature changed? Let's call that as delta T. The temperature change is 550 minus 50. 550 minus 50. That is 500 degrees Celsius. And what else is given to us is alpha. This linear expansion coefficient, we usually call it as alpha L. That's the symbol we use, and that's given to us as 17 times 10 to the power minus 6 Kelvin inverse. All right, this was the data, and now we'll try and use this data and somehow solve the problem. The first thing we will do is figure out a relationship between the changes in the length of, let's say, a wire. Let's begin with that. Let's not worry about the ring right now. Let's just imagine a wire, and let's talk about the changes in length of that wire, and let's see how that is connected to the temperature change and alpha L and things like that. So from the definition of alpha, or definition of this linear expansion coefficient, we could say that the change in length, delta L, that's going to be equal to alpha L, provided the wire is 1 meter long and the temperature changes 1 Kelvin, right? That's the definition of alpha L. However, what if we had, let's say, a wire which was 2 meter long? Then what would be the change in the length? Well, think of it this way. If you had 2 meter long wire, we could assume it to be made up of two 1 meter long wires, and then each one would expand by alpha L, and then the total expansion would be 2 times alpha L. Does that make sense? So similarly, if you had 3 times the length, then the total expansion would be 3 alpha L. So if you had L meter long wire, let's say, then do you see that the total expansion would be L times this number? Hope this makes sense. You just multiply by L. But again, this represents the change in length for 1 Kelvin rise. What if you had 2 Kelvin rise? Well, it would be double of this. 10 Kelvin rise, it would be 10 times this. What if you have delta T Kelvin rise? Ooh, it would be delta T times this. And so this is how we can connect changes in the length to change in temperature in alpha L. All right. So this is what we can use. Now you may think, well, this is all fine. This will work for a wire and everything, but we have a ring over here and we are asked to calculate the change in the radius of the ring. How do we take care of that? Well, you can think of a ring as just a bent wire, and the L over here would represent the length of this entire wire. And what is the length of this wire? Ooh, that is the circumference. So L would be 2 pi r for our case. So let's just substitute that. So for our case, we could write delta of 2 pi r. That would be equal to alpha L times the length is again, well, 2 pi r times delta t. But notice that when you're calculating change in 2 pi r, 2 pi is constant. It's not changing. I mean, how do you calculate change? You usually do a final value minus initial value, right? So it could be something like 2 pi r2 minus 2 pi r1. But notice 2 pi is common in that. So we could just pull this 2 pi outside the change, right? We could do that. So we could write this as, let me just do that over here so we can save space later. We could just write it as 2 pi delta r. Right? And now notice if you compare left and right side, 2 pi is common here and here. We can just go ahead and divide the whole equation by 2 pi. And so this will cancel out. And so notice eventually what do we end up with? We end up with delta r equals alpha L times r times delta t and just look at this expression that we just derived. That expression, can you see, is identical or analogous to this expression. The only difference is that L is replaced by R. And so now we can go ahead and plug in and solve this. But before we do that, I just want to give you one secret which can help us solve any problem like this. Notice over here, you may wonder again, oh, we had to do this derivation, and at least here it was a circle, so it was a little bit easy. Maybe tomorrow I'll get a sphere, or maybe a cylinder, or maybe some other complicated shape. How do I do this derivation? That could be complicated, right? Well, here's the secret. The secret is that this expression will work for any linear variable. What I mean is L over here is any linear variable. A linear variable is something that has the unit of centimeters or meters or inches or feet. So length literally does not mean length of some straight wire. It could be radius because radius is centimeters. So next time if you want to calculate changing the radius, just replace L with R. It could be circumference. It could be width of a cuboid. It could be breadth of a rectangle. So think of L in general as any linear variable, and you can just substitute. You can just skip all the steps in between. You don't really have to derive this in any problem. All right. So having said that, let's go ahead with this problem. Now notice that we know what alpha L is. We know what R is. We also know what delta T is. So we just have to plug in and figure out delta R. So whatever follows is just algebra. All right. Okay, let's do it. So alpha L is 17 times 10 to the power minus 6 Kelvin inverse times R. R is 200 centimeters. 200 centimeters. Let's just make a little bit room over here. I think this should be fine. All right. Times delta T. Delta T is 500 degrees Celsius. Another problem. Degrees Celsius over here, Kelvin inverse over here. The units are not matching. We need to now convert from degrees Celsius to Kelvin, maybe add 273, subtract 273 somewhere. Well, we have to be a little bit careful over here. In fact, there's a good news. Look, this 500 degrees Celsius is not temperature, it's the change in temperature. And guess what? The good news is the change in temperature in Kelvin is also 500. This is also 500 Kelvin. And let me show you how that works. Suppose we were to convert all the temperatures in Kelvin, we would add 273 over here. Oops. 273 over here. and a 273 over here, right? Degrees Celsius. That's how you convert to Kelvin. 0.15, but let's neglect that. But anyways, now when you subtract the temperatures and calculate the change in temperature, notice the 273 would just cancel out. So even if you were to calculate in Kelvin, you would get the same answer. You would still get 500 Kelvin. So we might as well go ahead and say this is 500 Kelvin. 500 Kelvin, and for that reason the Kelvin inverse and Kelvin just cancels. Everything is fine. We end up with the units of centimeters. That makes sense. We want the change in radii to be in centimeters. All right, let's just go ahead and calculate now. We have 17 times 10 to the minus 6 times 200 times 500. 5 times 2 is 10. And then we have 1, 2, 3, 4. 4 zeros. 1, 2, 3, 4 centimeters. Let's see what that gives us. That gives us, let's see, 1, 2, 3, 4, 5. That gives us 10 to the minus 1 when you multiply these two. Times 17 is 1.7. 1.7 centimeters. All right, so what we have done now is we have calculated the change in radius. But the problem, or the numerical, is asking me what's the final radius. All right, so one last step. Notice that the initial radius was 200 centimeters. Now the radius has increased. Change is positive. Notice the radius has increased by 1.7. So what's the final radius? I'm just going to write that down in this corner. The final radius is going to be the initial radius 200 plus 1.7. That's going to be 201.7 centimeters. And that is the solution to this problem.